Okay, this talk will just be very short overview, try to keep it to this time, and we do deep learning a little bit, and I'll try to give you a bit an overview on two modern aspects of text analysis, which are embeddings of words, and also longer sequences of text, and a bit on neural networks. So natural language processing at the moment is a very exciting area. I mean, it's one of the big challenges at the moment to make small steps to better understand all this text which is written, because like previous speakers have said, most of the important information in the world is stored as text. So it's very important to teach computers to better understand this text. Yeah, I stole this slide from the ETH natural language processing class. So like many challenges there in translation, in question answering, summarizing text, and eventually then teach the computer to have conversation. Although I don't like these people talking to their phones, but yeah, anyway. So, good, so as I mentioned, start a bit with word embeddings and then go to document embeddings, sequences of text. So the most important thing in machine learning approach is always to have very good features for how to give the data then to your system. It's called like feature engineering. So, and the easiest way to represent text numerically for a computer is this simple bag of words model. So let's just say there are 1 million words in the world. And so you just, if you have a big text and you have this word appearing in the text, then you will just put a 1 at that position of that word. So let's say it's the 5th word in our list, and that appears in our text, so we put a 1 in our vector, which has like many entries. And then this resulting representation we will feed into our system and use it for training. This works nicely, but it has disadvantages, so that it doesn't really capture like the meaning of these things. So the more modern methods try to find better representations of text, and especially in this case here of words. So that's what we want to look at. So what we want to find is we want to find a representation of one word, again the word number I, and represent it as a vector, like an array of numbers, and that should be like maybe, I don't know, let's find a point in 50 dimensions or so, and for each word, such that the points are kind of reflecting the meanings of these words. That's our goal. And it's not well specified. I didn't mention like what does it even mean to have this semantics of a word. But the high-level idea is like that words which have similar semantics, like whatever, king and queen, they should be kind of close together in this space when you just put these points in where they are, and they should be further away from words which come from very different topics. Okay, so how this is usually done? So I have to apologize to torture you with some math, so close to the well-deserved lunch. But what we want to do is we want to try to explain the words occurring together. So let's say the word I and J occur together in your text. We want to use this information that maybe they are related. So the way we're going to do this is that we're going to build this very big table of which word appears together with which other word in our very big collection of text. So you throw in all the text you have, and you build this matrix, and what I put there is I put the number of times these words did occur together, and if they don't occur together, then I just put a 0, or that's what's marked in gray in this table. And now what we do is we want to find these embeddings of each word. So this vi, this is a vector of like 50 numbers for each word. And the way we're going to do this, we want to find these vectors such that when I then multiply them together, then I get a number. Then I want to use that this number is kind of representative of the words occurring together. So I can try to approximate here the word I appearing with the word J 2 times. I'll try to make this number similar to the word I taking the inner product with the vector of the other word. So it's not, you can do this directly, or you can say that you want to approximate this function of this frequency, that they occur twice together. You can try to approximate that with the inner product. There are many variants of this. So this is not very new in general. So if you think that you want to approximate all the entries by such vectors, then what you get is like you have written your original matrix on the left as a product of two matrices. So that's what people call this a kind of a matrix factorization. So what I've written there is this V thing, that's the rows of that matrix. These are actually my word embeddings. So you can imagine if you take the ith word, which is these let's say 50 numbers which are marked in blue, and then you multiply this ith entry with the corresponding column in the other matrix, then that should give me the entry 2 in my co-occurrence matrix, in my input. So that's the idea. And this has been done before, so people have taken the co-occurrence matrix, so they have made this table for documents against words, then you get like a topic model, so then the vectors correspond to topics on one side, and the columns we correspond to the words. And here we've just done it for words against words. There is one important trick that we will now not do this for all entries, but we will only optimize these vectors, the V's, such that they observe the wide entries. Such only these we want to be approximated. And that's the main change which has changed these methods from the very classical ones, which are a few decades old, like the topic models and low-rank approximations like LSA and that. So to the more modern approaches, which are called like word2vec, and GLOV, which stands for Global Vector Representation something. So if you only approximate the wide entries, then here you get, for example, these word embeddings which are defined by the GLOV model. So this is the idea, and this all sounds very dry, so if I have internet, I'd like to show you some examples. Maybe I'll break the video again, sorry for that. Oh no, it actually works. So you can do all kinds of stuff. So let's say we can now have vectors for each word. So we just downloaded them from GLOV. You can get them pre-trained, you don't have to do anything. And now you have a point for the place Paris, and you have a vector for the Eiffel Tower. They're somewhere in space. And I can take this difference vector between 2 points, and I can attach it to another point, like, let's say I will attach it to the point of Switzerland. And then I could ask, like, now where am I in this space? So I've gone from Paris to the Eiffel Tower and translated this thing and attached it to Switzerland. So now what we have is we kind of asking which word would now be the corresponding thing semantically to the Eiffel Tower. So what's the Eiffel Tower of Switzerland? What would you guys think? So yeah, you're actually right. It's like the Bernese Alps. So that's the Eiffel Tower of Switzerland. So, sorry?
If you enter Hilton instead of Switzerland.
This is actually interesting. So it really depends like how you write the word. But you can actually find quite a deep things here. Yeah, I forgot what I wanted to search for. Like, so you can ask about a football player, who's the Zinedine Zidane of Switzerland. It actually works, kind of. So, yeah, you can put all these politicians, it's boring. And so you can have a lot of fun. ask who's the Carla Boni of Switzerland. Yeah, I did that wrong. And this is I don't know how that came out. And you can do the obvious things like... Okay, let's not get there. Okay, sorry. This is not a... Yeah, we wanted to talk about mathematics, so I have not tweaked this system anyway. We downloaded the pre-trained vectors. No tweaking, and if you want to play more with this, we have 2 screens outside. Yeah, that's how you find the embeddings of words, which you can then feed into a machine learning system to represent them better. And as you can see, these points, they capture the meaning of a word already quite well in some cases. Good. So actually, it's interesting that the very same mathematical model has also been used in recommender systems. It seems completely unrelated, but if you look at this Netflix, where people put 1 to 5 stars for the movies they like, mathematically, the systems which are good at that use exactly the same model. They try to find these 2 matrices such that their product approximates the wide entries. So you can use the same algorithms for that, but the main difference is that this recommender system stuff is supervised, so you need to have a lot of data of these ratings, whereas the cool thing about the text word embeddings is that they are unsupervised. You can just feed in as much text as you want. You don't need any labels, and this may be the main powerful idea of these word embeddings, and they have been very successful in various applications. Like now, whenever people use text, then the first thing they do is they transform it into word embeddings and then try to do something with them. There are many variants. I can recommend you to try it out. You can download code, but sometimes you don't even need code because you can also download the pre-trained word embeddings. It's not related to deep learning actually. It's just a different thing. It's just finding these 2 matrices basically. There are variants of it, of course, and it's still challenging to parallelize it on many computers. And a main disadvantage is that it's limited to words. You cannot apply it to sequences of words. So that's where the tricky part begins, and that I'll try to mention this a bit in the second part of, I don't know how much time I left. Yeah, so how to go to sequences. If you have several words, then the problem is that for each one we get such an embedding, we can use that. But the problem is all the sentences have different length, so we don't know how to then get a nice usable feature representation of one sentence. So here is an approach which can do that. What we do is we also use what we have seen for the word embeddings. So we take the sentence we have. So on the left, vertically, you can see this sentence. Whatever, wait for the video and don't rent it. So like 9 words. And we are writing the word embeddings we have constructed into the rows of this big matrix. So in this example here, we have like embeddings. Each word is represented as a 6-dimensional vector. You fill this into the table, the numbers you had, and now you try to transform it and such that you get a representation of the entire sentence. And the way we can do this is by learning a linear function of this of the input. So we take 18 numbers, which is like the red window here. For every entry there, you have a weight, a number which you try to learn, and you just multiply these numbers entry-wise with the input. This gives you one number as an output. That's called a filter, linear mapping. And then you use the same numbers you have specified for all the other positions, and you slide this rectangle from top to bottom. So when you slide this all the way through, then you don't have this big matrix anymore, but you have one vertical vector which has like 7 entries or 9 entries, whatever, as long as the text was. So one number for each word, basically, except the boundary. yeah, so then you have all these numbers, and now you have to transform them to make them fixed lengths. And what people do is they just take the maximum of all these numbers, and then they have just one number for the entire sentence, which is here. And then we can use this as a representation of the sentence. So it's not enough to just do this once. So we do this many, many times and just train the whole system. So the training consists in finding the best weights here for these linear functions and finding the best weights at the end, where we transform this representation. So here is a representation of the entire text. And then one goes into a linear classifier, say, to answer your final task, like is your text positive or negative. So how can you find the weights here and here? That's actually done by the chain rule, so by kind of back propagation of your output, which put as your training of the system. So in other words, what I described, which sounded very strange, is actually a neural network. So it's a neural network which just has 2 layers. It's not very deep. It has this, the first layer is called the convolutional layer, because the weights are the same from top to bottom. And the last layer is just some fully connected layer. So you put these together and you train it on supervised data, where you have to label your text, and then you find the best weights. Okay, so this approach is very widely used at the moment because it's kind of simple. We have not done any pre-processing of the text. There was nothing done, like no stemming, no negation processing, absolutely nothing. Just throw in the text and do this network, and it's quite robust. Also, it's relatively fast to train because on GPUs you can get a good speed up to train these convolutional filters, which we have used on the left side. There are many other approaches, so people thought that this year everything would be dominated by this very different architecture, which you have in the middle, which is called long short-term memory networks, which is also a nice thing, and the good thing there is it's unsupervised. You can feed in any text you want, and it's trained to reproduce the same text as you have fed in. So you can do it without labels. The problem is it just did not reach state-of-the-art performance in the applications we have looked at, and it's very slow to train in some applications, not so easy to do on a GPU. Also with paragraph to vec, which is a paper in 2013, people have been very interested in it, but it did not perform very, very well in most things that people have tried. Okay, in the last 2 minutes or so, I want to give you a use case, the application that we did. And so I want to show you a state-of-the-art system for a text classification task, namely to classify tweet messages by sentiment. And this is done by 2 master students of actually a joint project from ETH and ZAW, and the 2 students are here actually, they're Maurice and Jan. And they have done an amazing job, and they have actually won the Seminar competition of this year, which is the biggest competition in sentiment classification generally. So we have already participated 2 times before with like a bit older methods like SVMs. We're not so successful, but this year Maurice and Jan really killed it, and so we got the first place in 35 teams from 20 countries, which was very nice. And just to give you an idea of the task, so there are 3 labels. You have to say neutral, positive or negative, and here are the kind of tweets, so they are very messy, and it's not an easy task. I'm not responsible for the choice of team name, which was Swiss cheese, so you can blame these guys on that. Okay, we use exactly this architecture, which I described. But the key part is that you have to use more data because you don't have enough labels. We only have 10,000 labels from Senegal, or 20,000. So we have to use much more. So we processed almost 1 billion tweets to extract smileys from them, and then do this thing which is called distant supervision. So we trained the system on actually different kind of labels, which are smileys. This was invented by Alexei Severin, who is a researcher in Google Zurich. He did a really nice job with a similar system last year, but he used much less data than we did. And also we added more layers to it, which you can see actually only works if you have even more data. So I hope you're not feeling disappointed by the deep learning in the title, because what I've shown so far was only one layer, not very deep. But here we actually also added 2 or 3 convolutional layers. Just repeat what I described 2 or 3 times. And then you can see that the performance on the test set, which is here, actually goes up. So here you just use 4 million tweets, and here you use almost 100 million tweets. And you can see that that's actually about how much the state of the art has improved from last year to this year in similar architectures. Okay, and you can see that also changing the word embeddings using backpropagation helps a lot. So on the left, it's the initial word embeddings, and on the right, you see that how they actually change when you train the system. This is a plot made by Jan, and you can see that the words then end up clustered better by the meaning of their sentiment aspect. Okay, with that, I am done. There's a lot of interesting research going on to find things which are unsupervised, because whatever described so far is all supervised. We do not have a very good way to deal with unsupervised, or to use unsupervised information to find good document embeddings, whereas for the words, there is very good methods, not for sentences so far. The depth should be explored more, and there are interesting applications in all domains. And with that, I'm going to finish. And Jan and Maurice are here. They're actually looking for jobs if you want to hire them for a project. And if you want to play with this stuff, there's a lot of good open source libraries and data online. It's a very exciting area at the moment. And yeah, hope to chat to you in the break. Sorry for the overtime.
I think we have time for one quick, non-technical question, please. No, one question.
Thanks. So you said that LSTM didn't quite work for you. Did you try GRU, gated recurrent unit? What's your take on it?
So you asking about these recurrent nets, which are, yeah, everybody was trying it, but then in the competitions, it was not only us, but nobody had much success using RNNs. So all the good approaches in the competition use actually convolutional architectures.
So you didn't try much?
We tried a bit, but sure, one could try more, and maybe needs another year or so until they can be trained faster. I don't know. That was a very technical question.
Okay, thanks again, Martin. We proceed with our last talk before lunch.